Okay, so in the previous PowerPoint, you saw how come up with the bonding structure of molecules, really just specifically second row elements in hydrogen. Now what we're going to do is we're going to come up with variations of that and more general case. Like I said, we can have cases where you don't have atoms following the octet rule, and there's going to be other things that we have to take into account to help us determine chemical bonding structures. So here's a variation of the bonding. So as usual, we have count the valence electrons and come up with your skeletal structure. Now, in this variation, what you do is you start with the outside atom and you give it the number of bonds and lone pairs that you would expect. Now, from the previous slide, so hydrogen's on the outside, so we know hydrogen can have one bond. So give it one bond. So don't worry about the oxygen, okay? Then what you do is you count how many dots you have, all right? So there are 1, 2, each dash is 2, 1, 2, 3, 4. So there's 4 dots. Okay, and we need 8, okay? So we're short 4. Okay, the extra 4 will go on the center atom. So if you're short, after you fix the outer atom, okay, you give it its number of bonds and lone pairs, count the number of dots, and if they're short, you put the extra ones in the middle, okay, and you will put them as pairs. So you put 2 pair. All right, and you can see we're done, okay, and if you notice, it's the same structure as we had from doing our dot method. So the cool thing about this is that you don't even worry about the center atom when you came up with this, okay? Because it turns out oxygen will have 2 bonds, 2 lone pairs, and voila, it does using this method. All right, so let's do another one, carbon dioxide. So it has 16 valence electrons. Here's skeletal structure. So we're going to concentrate on the oxygen. Oxygen can have 2 bonds, 2 lone pairs. So you have your choice. You have this guy or this guy, all right? Well, we're not going to pick this one because if you did that, you'd have an oxygen with a bond sticking out off the side, okay? All right. And this would have to attach something. So we're going to pick the oxygen that only has one attachment, and that's this guy here. So I'm going to put that on. Okay. So the oxygen is taken care of. Now you count the number of dots. 1, 2, 3, 4, 5, 6, 7, 8. Each dash is 2. 9, 10, 11, 12, 13, 14, 15, 16. And that equals, so there's nothing left over. You're not short. So you're done. Okay. And if you notice, carbon has 4 bonds. Okay. I kind of like this method because it gives, I mean, it's really going to be how we're going to find things in the long run, especially when we do exceptions to the octet rule. So we don't even have to worry about the center atom. All right, let's try formaldehyde. So it has 12 valence electrons. Here's the skeletal structure. So I'm going to give the number of bonds and lone pairs to the oxygen, hydrogens. So oxygen can have 2 bonds, 2 lone pairs. I'm going to pick the one that has 2 bonds. I mean, it has only one connection, because if I picked this guy here, it would have an extra bond hanging off the side. Okay, each hydrogen has 1 bond, so you have here. Then count up the number of dots. Okay, 1, 2, 3, 4, 5, 6, each dash is 2, 7, 8, 9, 10, 11, 12. You're done. Okay. And if you look, oxygen has 2 bonds, 2 lone pairs. Carbon has 4 bonds. Each hydrogen has 1. Okay. Alright, let's try HCN. It has 10 valence electrons. Put your skeletal structure. Give hydrogen 1 bond. Give nitrogen 3 bonds and lone pairs. So you have these 3 possible. Okay, there's only going to be, so if you pick this guy, this nitrogen would have to connect to 3 things. This nitrogen have to connect 2, and this one connect to 1. We can see that nitrogen is only connected to 1 thing, so it's got to be this structure, this arrangement here. So we put it there, and this hydrogen here. We count up the number of dots, and we can see that it's 10. So we're all done. Okay, so what we're going to do now is we're going to look at some structures that don't follow the octet rule. And what we're going to do is we're going to use the method I just showed you. Not connecting the dots, but taking care of the outer atoms and so forth. So let's start. We're going to go use PCl5 and phosphorus pentachloride and sulfur dioxide to show this method. All right. So count the number of valence electrons. Phosphorus has 5 each. Chlorine has 7. So it's 5 plus 5 times 7 is 40. So so we need to have 40 dots when we're all done. Draw the skeletal structure. Okay, draw it like this or this, and it's good to draw it in a symmetrical kind of way. All right. So don't draw it, like this. So you try to always draw it kind of symmetrical. Next thing is just focus on the chlorine. Chlorine is in the same column as fluorine, so it's going to get 1 bond, 3 lone pairs. So do that for each chlorine. Okay, then count up the number of dots. Okay, so each dash is 2, so you get 2, 4, 6, 8, 10. 10 dots from the dashes. And then there's 6 lone pairs around each one, so that's 5 times 6, so there's 30 dots from the lone pairs, so there's 40 dots, and you're done. Now if you look at the chlorine, it has 8 electrons in the outer shell. 1, 2, 3, 4, 5, 6, 7, 8. Okay, but if you look at the phosphorus, it now has 2, 4, 6, 8, 10 valence electrons in the outer shell. Okay, so it doesn't follow the octet rule, but that doesn't matter because it doesn't have to, because it's in the 3rd row and it can have an expanded octet. Alright, so let's look at SO2. So SO2, number of valence electrons is 6 plus 2 times 6, 18. So there has to be 18 dots. Put sulfur in the middle. Give oxygen its number of bonds and lone pairs. So we're going to use the oxygen with double bonds. Okay, count number of dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, we're short 2. The short 2 the 2 extra go in the middle. Okay, now if you count up the number of valence electrons, each oxygen has 8, but the sulfur has 2, 4, 6, 8, 10. Okay, and again it can do this because it's in the 2nd row and the 3rd row. Okay, so why does expansion happen in the octet? When we develop the structure of a molecule, we put the least electronegative atom in the middle. If you notice, in SO2, there are 2 oxygens attached to the sulfur. The way that I think about this is the oxygens are very electron hungry, and each is sort of trying to tear away the electrons of sulfur. And so what it does is it kind of reaches in, digs out the electrons in sulfur and spreads them out into higher energy levels. The main thing is, remember, the rules are rules, but they can be broken because this is a dynamic situation. It's not static. Okay, it depends on who's connecting to who. It's not like taking Legos and connecting Legos. This is like taking Legos. If you take a Lego and it sees a different kind of Lego, it changes its shape. Okay, now before we go on, and we'll be studying more of these structures, let's take a bigger look at covalent bonds. We have seen that there's single, double, and triple bonds. At first glance, you might think a double bond might be twice as strong as the single bond, and a triple bond might be 3 times stronger than a single bond. But this isn't the case. And so let's take a look at why. Right. So remember, when bonds form, it's an overlap of the orbitals. Okay. So so when you have when shared pair, what you're having is a shared pair of the orbitals of electrons. So one reason covalent bonding stabilizes shared electrons because they share space between the overlaps of their orbitals. So orbitals are technically spaces where electrons can be. So when two orbitals overlap, it becomes more probable that the electrons are there and therefore more stable. We're going to look at 2 kinds of orbital overlaps, something called a sigma bond, and another one called pi bond. Okay. Sigma bond, and represented by the Greek letter sigma. Okay, and the way we're going to look at that is H2. Okay, H2. The bonding structure is simply H. Okay, and we can figure that out. Each, so if we did the dot method, we have 2 hydrogens, okay, and then what they do is they fill, and you get this structure, okay, which we can just represent as a single bond. Okay, so this structure, hydrogen H2, has a one single bond. So let's look at it more carefully. So each hydrogen has this, the OED, has this arrangement. It has an s orbital with 1 electron in it. Now remember that s orbitals look like spheres. I can draw it like a circle, but it's really a sphere. So when it bonds, what it does is it forms this, okay, which is actually an overlap of the 2 orbitals. So if we look at it more closely, the HK, this HH, with a circle around it, what we'll see is that the shared pair fall right between the 2 protons. Okay, so this is the shared pair somewhere in here. Okay, so they overlap. Okay, which stabilizes the electrons. And the other thing is the electrons are held between the 2 protons, and so they're really stuck in there tight. Okay, so these 2 protons sort of lock these guys in really good. Okay, so you have an overlap between the orbitals, green, and the electron is situated right between the 2 protons, locking them in place. Okay, so that's why this bond forms overlap and the interaction between the protons and electrons. And this is a sigma bond. A sigma bond is where there's a the overlap is between the protons, so it's internuclear overlap. So a sigma bond is internuclear overlap between the shared pair of electrons. Okay, and that's very stable. And it's really stable because of this connection, the electrons being stuck between the two protons. Okay, now there's other possible sigmas you could have. You could have an s orbital and a p orbital. Okay, remember a p orbital kind of has this figure 8 shape, and what they can do is they can overlap too. All right, so you can have one-sided dumbbell interact with the s, and that overlap can be between the two protons. So you can have an sp sigma bond as well as a SS sigma bond. So in the last example was a SS sigma bond. And also you can have two P's forming an overlap between two protons, and this would be a PP sigma bond. Okay, notice is that the overlap is always between the two protons. Okay, and that's what makes a sigma bond is that the overlap is between two nucleuses. And it doesn't just have to be a S, it can be a P, it can even be a D, and so forth. All right, the next type of bond is called a pi bond. All right, so let's take it's again, what for this case we're going to look at p orbitals. Okay, this won't happen for s orbitals, it only happen for p and bigger. And from the previous example, what we could see is that we could overlap two p's like this, and is that the overlap could be between the two protons, and that would be the sigmas. Well, there's another way you can overlap the p's, where they don't happen between the protons, and so you can overlap. So when you push these guys close together, what they'll do is they'll overlap up here and overlap here. Okay, they still have an overlap, so there's still a bond. Okay, but it's not internuclear. Okay, so this is less stable than a sigma bond. This should be sigma, because there's no protons, there's no internuclear attraction of the electrons. Okay, so pi bond is weaker than a sigma bond. They also tend to be shorter because well, just because of the way it's arranged here. Okay, the other thing is that because this bond, these two nucleuses are kind of close together, they will actually start to push away each other, and this bond could actually start to fall apart much easier than the sigma bond. All right, so and we're going to see that there's other reasons that why this bond will fall apart as well, and most of it has to do with the lack of interaction between the protons. Okay, bond length and bond strength. Bond length is dependent on what type of orbitals are overlapping from what types of atoms. For instance, comparing two s overlaps, a sigma bond of a carbon-carbon and a hydrogen-hydrogen. So if you had two carbons forming a sigma bond and two hydrogens form a sigma bond, the hydrogen-hydrogen would be a shorter bond and therefore more stable, okay, because they're smaller atoms. So if you have sigma bonds, the smaller atoms will form stronger bonds. Okay, an s orbital with a p orbital will be weaker because you have, so when you had this, so you have your nucleuses are farther apart and they won't attract. So an SS sigma bond will be stronger than a PP sigma bond because this length between the two protons is further apart. Now, shorter doesn't always mean stronger, especially when you get to pi bonds. Pi bonds are shorter than sigma bonds. Okay, but remember, they're weaker because there's no internuclear interaction. Okay, bond strength is also dependent on types of atoms. So if you had a carbon with a fluorine versus a carbon and a hydrogen, this is going to be a stronger bond because fluorine has a stronger interaction. So even though we draw bonds all the same, single lines or double, so forth, they can be stronger, longer, stronger or weaker. Okay, shorter, longer, stronger or weaker. Bond differences. So how does this pertain to single, double, and triple bonds? Without going into the details why, the following is understood about these. Single bonds are said to be simply one. So a single bond is simply a sigma bond. If you have a double bond, it will have one sigma bond and one pi bond. And a triple bond will have one sigma bond and two triple bonds. I mean, and two pi bonds. Okay. So it doesn't matter. So not every bond in a molecule is the same. So if you, for instance, if you see something like this, okay, one of these is going to be a sigma, doesn't matter which one, and the other one is pi. Now, if you get into organic chemistry, you'll really be spending a lot more time on this. Okay, pi bond stability. And this is important. Well, we related that it's going to be weaker than sigma bonds. But let's see what are sort of the consequences of this. Suppose we have two bonds, a sigma bond and a pi bond. So here's your sigma and here's your pi. And what you're going to do is you're going to have a fluorine atom fly by it and see how it affects this bond. Okay, so fluorine, which has a high electronegativity, they come in and it's going to try to break this, try to steal the electrons here. Now, it's going to be really hard because those electrons are really locked into place between the two protons. So fluorine is not going to really be able to break this bond. Now, if you took a fluorine and took it by a pi bond, it's going to be fairly easy for it to rip off those electrons, and now the fluorine could actually take the electron and become F minus. Okay, so when you have a pi bond, okay, either in a double or triple bond, it can be broken fairly easy. So if you have, so if you had like a carbon-carbon double bond, one of these guys is sigma, and it'll try to stick together, while the other one could be broken and maybe form a bond with another atom. So, and that's actually, we can take advantage of that to form new molecules. All right. So again, if you take organic chemistry, what you'll see, you'll start out with a molecule with double or triple bonds. You add a higher electronegative atom to it, and with that electronegative atom will basically tear the electrons off and form a new molecule. Okay, another thing that I want to go over is that the two electrons in pi bond and a double bond can actually move when they are in a molecule. Because they are unstable, they can be pulled away into the valence shell and replace replace bonds. Okay, especially if it's a pi bond with a high electronegative atom like oxygen. So oxygen will have this case here, two bonds, two lone pairs. Okay, but and so one of these guys is a pi bond, and what that pi bond can do is that it can be drawn on the outside, and because it's weak, because it doesn't stick between the atoms all that well, it can move to the outside. All right, and so you'll see oxygen often when it has a double bond, it can form this structure as well. Okay, you're going to have to remember this because this is, it flips back, it can flip back and forth between a double bond and two lone pairs and a single bond and three lone pairs. But if you know, it's the same amount of electrons. So it's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So they can flip-flop. So pi bonds can flip-flop if they're on high. Okay, now I wanted to have a clarification here. Let's look closer at the bonded oxygens below. So when you have this case here, it really means you have this. There's 6 valence electrons of oxygen plus 2 valence electrons of another atom. All right, so one of these here, okay, actually belong maybe like to carbon or something. Remember, one of these electrons, well, you get 2 pairs that are shared between, so they're 2 shared pairs. 2 of them belong to the carbon, 2 to the oxygen. Oxygen has 6 electrons normally. Okay, but if you look at this case now, the oxygen now actually has, it has actually sort of gained an electron. So no longer does one of these electrons belong to carbon, now it belongs to oxygen. And so oxygen now has a negative charge because it's taken one of these electrons, so it's gone from okay, let's say that this pair right here, so we'll say that these two right here are from the carbon. Okay, whoops, start over. Okay, so here's your normal oxygen 2 bonds. Here are 2 bonds and the 2 lone pairs. Now let's say that these two are this is carbon hydrogen, carbon and oxygen, and carbon and oxygen. Now in the new way it forms, okay, in a sense carbon has lost a bond, electron, and oxygen has gained an electron. So whenever you see this case, it actually means that the oxygen has actually become a negative charge. So if you see oxygen like this, we put a negative charge on it because in a sense it's gained an electron from the carbon or whomever. So So if an atom has a negative charge on it, any atom, okay, so if you have, for instance, let's take a look at, compare fluorine F minus to bromine F minus, okay. All right. Okay, fluorine F minus, Br minus. So fluorine is a relatively small atom and bromine is a larger atom. They both have a negative charge on it. Okay, this negative charge. So in the case of this, bromine would have a lower charge density, because you can think of charge density as charge per volume. So this would have a lower charge density than fluorine. So basically what happens is you can think of this negative charge being spread out over a larger volume and versus the smaller volume here. Okay, so we call this charge density. Spreading the charge out over a larger volume. When this happens, there's no single spot to find the charge, and it gets spread out enough that charge is virtually invisible or hard to find. So in this case, it's really easy to find the electron. Over here, it's harder to find because it's spread out. Okay, so think of it this way: maybe an Easter egg hunt. If all the eggs were sitting in the middle of the room, you could easily get to them. But when they're spread out, it's hard to find them, in a sense, making them more stable because you can't find them, all right? And they'll stay what they are. Okay, so if you can spread out the charge density of a charge, you can stabilize that charge. Okay, so if we go back and look at oxygen, when it flips, it goes from 2 bonds, a double bond and 2 lone pairs, to a single bond and 3 lone pairs. What happens is the charge density essentially becomes reduced, okay, because they're flipping back and forth, and it's harder to find the electrons. So molecules will often find ways to reduce their charge density so that they can become more stable. We'll see that charged molecules like polyatomic ions have very low charge density, and that's because they're very large. Therefore, it's harder to take their charge away, and it's also harder for those molecules to interact. For instance, phosphate, okay, is a giant molecule, all right, compared to most ones. It has, that's not giant, but it's a big molecule. It has 5 atoms, okay, and there's 3, so it's PO4 3 minus. Okay, and that 3 minus ends up getting shared all around this molecule. Okay, and we'll see how that works. And when it does that, it's harder for this molecule to lose. Okay, the next thing we're going to look at, all right, is formal charge. So right now we looked at bonding, structure, okay. We looked at different types of bonds, sigmas and pi's. Briefly we talked about charge density. Okay. So we can see that when we draw a structure, it's not just a simple, when you write H2O, okay, it's maybe not as simple as just this arrangement here, okay? There's a whole lot going on here, all right? And then so what we're looking at is that. So the next thing we're going to look at is called a formal charge. So how the shared electrons are distributed in a bond is determined by electronegativity of atoms. So I said is that you have HF, which is HH, okay. You can see that the electrons, the shared pair, will be pulled towards the fluorine more than it would to this hydrogen because of electronegativity. And we will look more closely at this at this type of thing, and PowerPoints come up. Okay, each atom in a bonding structure will have what we call a formal charge, Fc, and it's determined by how many bonds it has and how many lone pairs. And here's the formula, and it's written different ways, but this is the way I like to write it. The formal charge is equal to the number of valence electrons minus the number of dashes minus the number of dots. Okay, so we're going to go over some figuring out the formal charge of some atoms and molecules. So let's look at water. So we're going to figure out the formal charge for each atom here. So formal charge of each hydrogen. So hydrogen has one valence electron. There's one dash, and there's no lone pairs on the hydrogen. I mean, no dots. Okay, so it's going to be 1 minus 1 equals 0. So this has a formal charge of 0. Each one. So in the oxygen, it has 6 valence electrons. There's 2 dashes, 1, 2, and there's 4 dots. Okay, so it's 6 minus 2 equals 0. All right, the formal charge for on each atom of formaldehyde. For each hydrogen is going to be number of valence electrons, 1, minus 1 bond or dash, minus no dots, equals 0. Oxygen, okay, 6 valence electrons, subtract 2 dashes, subtract 4 dots, 0. And carbon has 4 valence electrons, 4 dashes, no lone pairs, 0. Okay. The sum of the formal charges will equal the charge on the molecule. So these two molecules had a charge of 0. Okay. A formal charge is not an electrical charge. It is kind of a relationship between the atoms. If an atom has a negative formal charge, it usually might mean that it has more electrons of the shared pair. Okay, doesn't have to mean, but it helps us figure that out. Okay, so you'll have to be able to figure out formal charges. Okay, all right, so let's go back and look at sulfur dioxide. So sulfur dioxide, we came up with this structure here, all right? Remember, sulfur didn't follow the octet rule, and that was the previous, that was in the earlier slide. However, we learned is whenever you have a double bonded oxygen, you could also write it out as a single bond with 3 lone pairs. Okay, so you can write sulfur dioxide as this here, 1. You could write it like this, where one of the oxygens has the 3 lone pairs. Remember, put the dash here. Or you could have the other oxygen have it, or you could have both of them. If you count up number of dots, all of them have the same amount of dots: 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so each one of these has 18 dots around it still. So A and B look quite a bit alike, all right? But they're still different because the the charge on the oxygens on our different atoms. Sometimes double on the left oxygen, sometimes it's on the right. So here it's on the right, and here it's on the left. Now, so when you can do is you can have these guys can flip-flop back between each other, and when they do that, we call this a resonance structure. So if you have two structures that look identical in terms of their connectivity, but where the double bonds are, etc., they are essentially not the same structure, but we call a resonance structure. They sort of bounce back and forth. They like echo between each other. That's why we might call it resonance. And resonance is a really important factor we're going to see. Because what it's going to end up doing is it's going to end up spreading out charge. So we have four possible structures. I mean, three possible structures, really. Four structures, but really only three. You can have the one we started out with, one where you have no double bonds, and one with one double bond positioned two different places. So it has three structures, where one of them is a resonance structure. Okay, now comes the interesting part. So if you can have these four different structures, really three, is there one that's better? Okay. And if it is, which one is it? And that's what we're going to try to figure out. And well, that's what we are going to figure out. Okay, determine the most probable structure. Okay, so we're going to be looking at a sulfur dioxide to figure out which one of those structures, those three structures, okay, is probably the one that exists for most probable for sulfur dioxide. So there's going to be three things to look at. We're going to look at the formal charge, and structures with little differences in their formal charge are preferred. We'll be looking at resonance structure. Resonance structure is a real strong reason for stable structures and therefore being probable. And the reason why resonance structures are strongly preferred because they delocalize or spread out charge density. And then the third one is the octet rule. Due to quantum considerations, if an atom has an octet, it is usually better. Now, and it's not because of octet rule or anything like that, it's just it has to do with quantum considerations. The priority of these three is resonance structure is always the best, octet rule, and then formal charge. Now these can vary, but these are just a good place to start. And so what we're going to do is we're going to look at each structure compared to resonance structure, octet rule, and formal charge, and try to figure out which one of them, which structure is the best based down. So in the first structure that we came up with two double bonds, the formal charge for the oxygen is going to be, remember, let's take that out. So the has 6 valence electrons. It has two bonds and 4 dots. So formal charge is 0. A sulfur also has 0. Okay, it has valence 6. 4 dashes, 1, 2, 3, 4, and 2 dots, 0. And each in the oxygen 0. So it has no formal charges, which is good. You don't like to have lots of formal charges, negatives and positives. Now, this does not have a resonance structure. Okay. And as far as the octet rule goes, is the 2 oxygens have octets and the sulfur doesn't. Right, the second structure, where we came up with each sulfur had single bond. So here what we did was we moved the double bonds of the oxygen, each oxygen, out as a as a single bond and 3 lone pairs. So we're going to figure out the formal charges first. So each oxygen has 6 valence electrons, 1 dash, and 6 dots. So it has formal charge of -1. So it has a -1 here, -1 here, and the sulfur has a +2. Okay, this is not a very good situation, all right, because there's too much formal charge battering around, all right. Nature doesn't like to have separation of charges. It likes to have equal charges if possible. There's no resonance structure, and the oxygens have octets, but the sulfur doesn't. Okay, so let's look at the third structure. The third structure, the formal charge. So this is the resonance structure, where you could have a double bond in either oxygen. The formal charge of the double bond oxygen is going to be 6 valence electrons, subtract 2 bonds. I'll subtract 4 dots. So 0. For the single bond, it's going to be 6 valence electrons, subtract 1 dash and 6 dots. It's a -1. And the sulfur has 6 valence electrons, 3 dashes and 2 dots for +1. Okay. Now, one of the things about formal charges is some of the formal charges has to equal the charge on the molecule. Sulfur dioxide has no charge on it. Therefore, -1 plus +1 plus 0 is 0. Okay, so that's a check. And over here, this would be 0 plus 1 minus 1. All right. So it has formal charge, but it moves. And that's kind of an important thing, because on the previous example, where you had this guy here, number 2, is that all these charges were stable. I mean, they just static. I mean, not stable, static. And these ones are dynamic. And that's so anytime you move charge, it makes it stable as well. Okay, because it's harder to find electrons. It has resonance structure, and all the atoms have an octet. So this oxygen 2, 4, 6, 8. Sulfur has 2, 4, 6, 8, and oxygen 2, 4, 6, 8. All right. So now let's compare the 3 structures in terms of these 3 things: formal charge, resonance, and octet. So the very first structure, one with just double bonds. I'm going to leave off the lone pairs here. That had no formal charge, which is good. The resonance structure, well, let's just stay with formal charge. The second one had 3 formal charges, which is not great, because you have a lot of charge spread out. I mean, there's a lot of charge here. Okay, so this is not really very good. Okay, and then the last sample, you have 2, which is not good, but it's spread out. Okay, so it's not bad. All right, so I'll put NB for not bad. All right. So far, number 1 is probably the best of using formal charge. In terms of resonance structure, the first structure and the second structure had no resonance structure, and the third structure had resonance structure. So this is really good. So this is good. All right, in terms of octet, the first 2 structures had 2 octets, and the third one had 3 octets. So this is good. So overall, it looks like number 3 structure is probably our best. Okay, has resonance structure, which spreads out the charge of the charge being on different atoms. Okay, moving between atoms, that all stabilize it, and then it has octet. Okay, now let's look at carbonate, CO3 2-. So we're going to find the basic structure first. So you have to count the number of valence electrons. So 4 from the carbon, 3 oxygens, 3 times 6, plus 2, because that's a 2 negative charge. Add them all up, so you have 24 possible electrons. 24 valence electrons. The 2 on carbonate. So draw the skeletal structure. Give the oxygen a number of bonds and lone pairs. Okay, because the outer atom, 2, 4. So each oxygen gets a double bond. Okay, don't give it a single bond. Okay, remember carbon can have 2 bonds, lone pairs. But if you just made it a single bond, they would have a extra bond hanging over here like this. Okay, and this is not good. All right, so you use the double bond version. And you do that for all 3 of them. Okay, now they count the number of dots. Each dash is 2, 2, 4, 6, 8, 10, 12. So there's 12 dots from the dashes, and then there's 2, 4, 6, 8, 10, 12 dots from the dots, so you have 24. Okay, so this looks like this might be the structure. Okay, but is it? Okay, so we just can't draw things. Okay, we can draw it out. What we have to do is, does it make sense? Oops, no it doesn't. So let's take a closer look. Notice that carbon has 12 valence electrons. So the way I have it drawn right here, there's 2, 4, 6, 8, 10, 12. Carbon is in the second row. It cannot have more than 8 electrons. Okay, it can't have an expanded structure. So what you have to do, and it's not hard, is you simply can manipulate the double bonds out onto the oxygen. Okay, so what we're going to do is move one of the bonds in double as a lone pair. Okay, so we end up getting this structure. We could do that for 2 of them, and we'll see that we have a structure now that fits the bill. Okay, doesn't break any rules here. Carbon has 8 electrons in the outer shell. And all right. So when you come up with the structure, especially if it's second row, you may have to manipulate the method. All right. So now let's see if this has more than one structure. It's like water, for instance, only has one structure. You can't draw it, and you can't have anything like this. Okay. So there's not going to be any moving of electrons. Okay, but sulfur dioxide, we saw that we could move electrons. Remember, anytime you have an oxygen, the double bond, you can move the electrons and get another structure. Okay, so those that have other structures. Okay, there are 2 structures here. So we have, this is our original structure, but what we can do is we can move that double bond around. Okay, we could put it here, and we could put it here. Okay, so the structure that we wrote on the previous slide can actually flip between 3 structures, and so this is a resonance structure. Okay, now there is another possible structure where the double bond comes out and forms all 3 oxygens form 3 lone pairs. Okay, so we have 2 possible structures, and we want to figure out which one is the best. Okay, all right. So let's compare the 2 structures. So the formal charge on the first one, on the resonance structure, and we'll just draw one of them. Okay. All right. So the formal charge on a double bond. Okay. It has 6 valence electrons, 2 dashes, and 4 dots. So its formal charge is 0. So that has 0. And formal charge in each single bond, 6 minus 1 minus 6 is minus 1. And a formal charge on the carbon is has valence electron 4, 4 dashes, and no dots. So its formal charge is 0. Okay, now remember, the sum of the formal charges should equal the charge of the molecule. The molecule is CO3 2 minus. So the sum of the formal charges should be 2 minus, or minus 2. So we have a minus 1, 0, minus 1, and 0. And sure enough, it's minus 2. Right, and so it has 2 formal charges. It has resonance, we saw that. And notice all the atoms have octets. Okay, this oxygen has an octet, 2, 4, 6, 8. This oxygen has an octet, 2, 4, 6, 8, 2, 4, 6, 8. And the carbon also has octet, 2, 4, 6, 8. Right, structure number 2. They had 3 single bonds and 3 lone pairs. Okay. Now, one thing you notice about this is that carbon only has 3 bonds. That's fine. Okay. An atom can have less bonds than it requires. Okay. But it can have more. So the second row can have up to 8 electrons. Okay. So carbon can have up to 4 bonds. It could have 3 bonds, 2 bonds, or 1 bond, all determined on the situation. So even though it doesn't look like it, you're going, oh, I'm going to throw this out because it only has 3 bonds. Don't do that, because it's okay. It's okay. All right. It's if it had more, if it had 10 valence electrons, then you would worry about it. So let's just stick with it. So the formal charges, each oxygen is 6 minus 1 dash minus 6 dots, or minus 1. Okay, the carbon has 4 valence electrons, 3 dashes, and no dots, so it's plus 1. Okay, now you can see that this is not going to be a very good situation because there's 4 formal charges. This has 2, so this already is not a good thing. Has no resonance, and the oxygens have octets, but the carbon doesn't. So structure 1, okay, this structure up here has 2 formal charges, and number 2 has 4. So this is no good. This has resonance, so this is good, and this has 4 octets, so this is good. So this is our preferred structure up here. Okay, resonance structures are very, very important. A resonance structure, as I said, spreads out the charge. In a sense, it decreases the charge density. It also stabilizes pi bonds. And the way it does that basically is by spreading out the electrons that are in the pi bond. Stabilizes charge in that other atoms can't take them. So when it spreads out the charge, it's hard for other atoms to come and take the electrons. All polyatomic ions have resonance structure, and this is why they exist, is because they have resonance structure and makes them stable. Okay, if you go into organic chemistry, you'll be talking a lot about resonance. Okay, oddballs. Sometimes our techniques don't always pan out. in coming up with bonding structure of a molecule, we tried to make sense of this without any magic hand waving, such as just the octet rule. See, the way that I did it, I put the least electronegative atom in the middle because other atoms try to eat away at it like a vulture. The outside atoms are like the vulture, okay? And what they try to do, in a sense, is fill their valence shell. And I'm not really sure behind it, but I'm sure there's a strong quantum mechanical method to explain it, and not just saying octet rules. Okay, but this falls apart when they try to explain why octet rule doesn't work. Right, so most time people talk about, when your normal chemistry class, they'll talk about the octet rule, then they'll talk about expanded octet, and really don't know how to explain it. Okay, we don't even try to say we need to have an octet. We allow for octets, expanded octets to happen, okay, just by doing the method I came up with. So I didn't say you need to have 8 electrons around each atom. I said what you need to do is have the outer atom have the number of electrons that it would have if it was in the second row, which usually means is that the outer atoms will have octets, and not always the center atoms. So what I'm going to do is there are things that just don't make sense, and I want to go over this. And one of them is carbon monoxide. So carbon monoxide has 10 valence electrons, 4 from carbon and 1 from oxygen. So carbon's least electronegative atoms, and so let's give oxygen its number of bonds and lone pairs. So here you go. Let's give the oxygen 2 bonds, 2 lone pairs. Now count them up. Get 2, 4, 6, 8, and there's so there's 2 missing. So we're going to put the 2 on the carbon. Okay. Now, what can happen here is that this double bond is that you can move that double bond out here. So one of the pi, so one of these is sigma, one's a pi. The sigma bond can come out and be a lone pair, but it also turns out that it could go the other way and come out on the carbon. Okay, so it could either look like this, well, actually not. So, or what can happen is one of these guys can go in here, and so this gets complicated in terms of trying to figure this out. So it's possible you could also have a structure like this. Sorry, you could have one that looks like this. Okay, I mean, it still has 10 valence electrons, okay? So you can have this case, you can have this case, you could possibly even have this case, and you possibly even have this case and this case. So there's 4 different possibilities. All right, it still has 10. So you come up with moving all these electrons around, and you can come up with actually 5 different ones. You can come up with okay, and so what we want to do is see which one's the best. Normally you won't have to do this. I just want to show you that this can be done. So structure number 1, the formal charges are going to be for the oxygen 0, and for the carbon 0 as well. So 4 minus 2 minus 2 0. So this is good. This has no resonance structure, and there's 1 octet right here. Okay. Number 2, the oxygen has 1 minus, and this carbon has +1. So 4 valence electrons, 1 dash and 2 dots, plus 1, and oxygen. There's no resonance structure. Okay, enough to flip back and forth, and 1 octet right here. Structure number 3. Oxygen has plus 1, carbon has minus 1, no resonance structures, and 2 octets. Okay, now this is going to be odd, all right, and this one's actually kind of good because you have 2 octets, but it's kind of odd because of this. Okay, number 4, the oxygen has plus 2 and minus 2. Okay, 6 minus 2 dashes minus 2 dots, plus 2. Carbon, 4 valence electrons, minus 2 dashes minus 2 dots, minus 2. No resonance structure, and 1 octet. And finally the last one, plus 1 on the oxygen, 6 minus 1 dash and 4 dots, and carbon, 4 minus 1 dash, no resonance, and no octet. So will this give, so can I figure out which structure is preferred from these 5 using this information? Okay, so as far as formal charge goes, number 1 is probably the best because there's none. Okay, none of them has resonance structure. Number 3 has 2 octet. Okay, so which one is the best? Okay, so I told you that it went resonance was better than octet, which was better than formal charge. So since resonance is there's no resonance structure, this is probably going to be the column that's going to really push things. Okay, this has 2 octets. Therefore, we're going to pick the structure that has 2 octets versus the ones that have less than that. Okay, this has a plus 1 and a minus 1. Okay, formal charge, but the octet kind of cancels it out. So the weird thing about this structure, though, so this is the one with the triple bond. Okay, weird things about it is carbon has 3 bonds. Okay, and I told you that doesn't matter. All right. Whoops, this should be. Sorry, rewrite it. Okay, so it's weird for a bunch of reasons, but one of it's good because it has 2 octets. Carbon and oxygen both have 4 electrons in the outer shell. But it's weird, first of all, is that oxygen has a plus 1 and minus 1. Usually you want to have the negative formal charge on the most electronegative atom. In this case, oxygen is more electronegative, so you would think that this would be the negative. The other thing that's odd, though we didn't really, doesn't matter, is that it doesn't follow the pattern. Carbon usually has 4 bonds, no lone pairs. Here it has 3 and 1. Oxygen usually has 2 bonds, 2 lone pairs, and here it has 3 and 1. Okay. So when you come up with structures, you have to really think about it, and it's just not a thing about making the octets work. So you really have to sort of distill what's the best. Okay, to tidy up. So to give it a chemical formula, we can figure out the bonding structure. And the way that I told you come up with it is come up with a skeletal structure, count number of valence electrons. The outer atoms will get the number of bonds and lone pairs as the second row element associated with it. And then if there's if you come up short with the dots, you can put the dots in the center. And so we say nothing about following the octet rule doing this. We basically come up with the structure based on this. Then we talked about two different types of bonds, sigma and pi bonds. Okay, sigma are stronger than pi bonds. If you have a pi bond with on a higher electronegative element, the electrons of pi bond can move out as lone pairs, and that's going to be an important thing, especially in the resonance. Then we talked about formal charge, and then resonance structures, and then if you're given, if you can figure out different structures, you can figure out the best structure based on resonance structure, formal charge, and octet. Okay, so what we're going to do next is we're going to see how this applies to the actual three-dimensional structure of these molecules.